welcome to the deep dive. Today, we're going to be looking at this new research you sent over about the future of data storage magnetic octupole memory.
Oh, yeah, this is a fascinating one.
It really is, and a bit mind-boggling, honestly. Sounds like we're on the verge of a major technological leap, maybe?
It does. It really does. It's got that science fiction feel to it.
Yeah.
But the science behind it is really solid.
Okay.
And yeah, the implications, they're pretty huge.
Okay, so I think most of our listeners are familiar with the limitations of traditional hard drives.
Right.
There's mechanical, they're slow, they break down.
Hmm.
So where do these domain wall devices fit into all of this? Is this kind of the next step?
Yeah, so scientists have been working on ways to store data by moving these tiny magnetic boundaries within a material
Okay.
instead of relying on those physically spinning disks.
So instead of a spinning platter, we're flipping tiny magnetic switches.
Yeah, that's a good way to think about it.
That does sound promising. But I have a feeling it's not quite that simple, right?
You're right. It gets a little bit more complicated.
Sure.
The early attempts at these domain wall devices, they used ferromagnetic materials, where all those little magnetic spins are kind of all aligned in the same direction.
Okay.
But they had some serious drawbacks. They used a ton of energy, and they generated these stray magnetic fields, which really limited how much we could miniaturize them.
So that's the issue then. So if you want to pack a lot of them together on a chip or something like that,
Right.
they'd interfere with each other.
Exactly.
What a roadblock.
Yeah, it was a big challenge.
So where do we go from there?
So researchers started to investigate antiferromagnets.
Okay.
And in these materials, the spins are arranged in opposite directions.
Yeah.
So they actually kind of cancel each other out.
So antiferromagnets have a very, very weak magnetic field.
Exactly.
So they're perfect for creating these smaller, more efficient devices.
That was perfect, right?
Yeah. So what's the catch? There's got to be a catch.
Well, the catch is that the very thing that makes them so attractive, those weak magnetic fields, also makes them incredibly hard to control.
Oh, okay.
It's like trying to herd cats that are invisible and can move at the speed of light.
That does not sound easy.
No, not at all.
So how did they crack the code? How did they figure out how to get around that? Is this where the octupoles come in?
This is exactly where the octupoles come in. Yeah. So the researchers used a very specific type of antiferromagnet that forms these clusters of magnetic moments called magnetic octupoles.
Okay, I'm going to need some help visualizing this. What is a magnetic octupole?
So imagine 8 tiny little compass needles, and they're all pointing inwards toward the center of an invisible cube.
Okay.
That's kind of a simplified way to picture a magnetic octupole.
So not your average bar magnet?
No, not at all.
And these octupoles are the key to controlling antiferromagnets.
They are, yeah. So the research team, they were able to move these octupole domain walls at unbelievable speeds.
Oh, wow.
We're talking 750 meters per second.
750 meters per second. That's, hold on, that's incredibly fast.
It's mind-blowingly fast. And that's not just like a little speed boost.
Mm-hmm.
We're talking about potentially tenfold increases in data access speeds. To put that in perspective, imagine loading a massive video game in seconds, not minutes.
That's incredible. But before we get too carried away daydreaming about instant video game loading, let's talk about, what this actually means.
Right.
We've gone from these clunky spinning disks to these lightning-fast octupole domain walls.
Mm-hmm.
What does this mean for the average person? What are the real-world applications of this kind of discovery?
Well, I think the potential impact is enormous, and it really touches every aspect of our digital lives. Smartphones, laptops, data centers, they all rely on memory, right?
Right.
And this new technology has the potential to revolutionize all of them.
Okay, so let's dig a little deeper here. Yeah.
You were talking about how this could revolutionize smartphones and laptops and data centers.
Right. Yeah. So many different applications.
Yeah. So where should we start with this? Let's zoom in on some everyday devices.
Yeah. Good idea.
How would this new memory change how things work?
So imagine a world where you pick up your smartphone and it boots up instantly. No more waiting around.
Oh, wow.
And then you can run all those complex apps and it doesn't just drain your battery in an hour.
Right.
Or think about a laptop that can handle those really demanding tasks like video editing without even breaking a sweat.
Yeah, that would be, I mean, that's kind of a game changer,
It
right?
really would be, yeah.
For so many people, I know
Yeah.
I think we've all experienced it, right? Like your phone gets older and it just gets slower.
Mm-hmm.
And it's so frustrating.
Yes, definitely.
Is that something this technology could address?
Absolutely. I mean,
Yeah.
one of the big advantages of Octupole-based memory is its energy efficiency.
So these systems, they wouldn't need to work as hard to access and process data, which means less wear and tear on the hardware. They could last much, much longer.
So longer lasting devices, which means less e-waste too.
Exactly. It's more sustainable in the long run.
Okay. Well, that all sounds great for, your personal devices.
Right.
But what about those larger systems? What about data centers? They're massive energy hogs, right?
They are, yeah. Data centers consume a huge amount of energy.
Yeah.
And a lot of that goes to just powering those memory systems that store and process all that data.
So switching to Octupole-based memory, that could make them a lot more sustainable.
That's the idea.
Yeah.
If we can make these memory systems significantly more efficient, we could dramatically reduce the energy consumption and environmental impact of these data centers.
That's a win for everyone, really. It's kind of fascinating to think about something happening at such a tiny scale, like, these microscopic magnetic structures are having this huge ripple effect, right?
I know, it's amazing. And it really underscores how important fundamental research in materials science is. I mean, these kinds of breakthroughs can have far-reaching consequences.
Yeah, and it's interesting, too, that you said the research team, they were actually surprised by how well this worked.
They were, yeah. They weren't even sure if using octupoles would even be feasible.
Wow.
But they decided to give it a shot, and it really paid off. I mean, the results exceeded all their expectations.
That's an incredible story. It makes you think what other kind of hidden gems are out there in the world of materials science, just waiting to be discovered, right?
Absolutely. I mean, there's a whole universe of materials out there with these unique properties just waiting to be explored. And who knows what kind of incredible technologies we'll uncover in the process.
Yeah. This deep dive into the world of magnetic octupoles and the future of memory technology has been incredible.
It has been, yeah.
But before we wrap up, I'm curious, what are some of the challenges that researchers still need to overcome to make this mainstream? What needs to happen to get this, into our phones and our computers and our data centers?
That's a great question. And it's important to remember that even with these impressive results, there's still a long way to go before magnetic octupole memory is commonplace.
Okay.
But we can definitely talk about those challenges.
Let's do it. I'm really interested to hear more about that.
Yeah.
Okay, so what are those challenges? What are we looking at here? What's standing in the way of this?
Yeah, so we talked about scalability, and that really is, I think, the biggest hurdle.
Okay.
It's one thing to create these magnetic octupole structures in a lab under very controlled conditions, but the whole other ballgame to try and mass produce them at a cost that makes sense, for consumer electronics.
Yeah. I mean, you're talking about taking these tiny microscopic magnetic structures and somehow manufacturing them by the millions or billions?
Exactly.
That's going to be unbelievably complex.
It is, and you've got to maintain that precision, that quality at that scale, right? I mean, if even a small percentage of those octupole structures aren't formed just right, it could really affect the performance and reliability of the whole memory device.
Yeah, so it's like one weak link in the chain can bring down the whole system.
Exactly, yeah.
So what are researchers doing to try and overcome this scalability challenge?
Well, they're looking at a bunch of different approaches, new fabrication techniques, different material combinations.
Okay.
It's a lot of trial and error right now. It's like a puzzle, trying to find the right pieces that fit together perfectly and can work on a huge scale.
Okay, so you've got scalability. What else is there?
Well, we touched on integration earlier.
Yeah.
How will this new type of memory actually interface with the systems that we have now?
Right.
Our current computer architectures, they're optimized for the types of memory that we use today. To really get the full benefit, the speed and efficiency of octupole memory, we may need to rethink how we access and process data in the entire system.
So it's not just a matter of swapping out one memory chip for another. It's bigger than that.
Yeah, it's a much bigger undertaking, and it requires a lot of collaboration, between material scientists, computer engineers, software developers.
Okay.
It's a multidisciplinary kind of thing.
All right, so you've got scalability, integration. What about reliability? You were saying these devices need to be able to handle the bumps and jostles of the real world, how do we know that this memory is going to be as robust as what we're used to?
Right. Well, that's where rigorous testing comes in.
Okay.
Researchers are putting these devices through the ringer, Temperature extremes, vibrations, electromagnetic fields. They want to make sure they can hold up under pressure.
So stress testing them to find the breaking points and then reinforce them.
Exactly. That's the idea.
Okay, but even with all that testing, I mean, is there always a chance that something could go wrong, something unforeseen could pop up?
Of course. I mean, that's always a possibility with any new technology.
Yeah.
Especially when you're dealing with something this complex.
Right.
There might be challenges we haven't even thought of yet.
Yeah, yeah.
But the research teams, they know this, and they're working hard to identify and address any issues as they come up.
So it's a constant process of like testing and refining and adapting as you go.
Absolutely.
It sounds like there's a lot of work ahead before we actually see this in our phones and our laptops. But even with those challenges, I mean, you can't help but be excited about the possibilities here.
Oh, absolutely. This is, it's a potential game changer. This technology, it could completely change how we think about data storage.
Yeah.
And while it might be a while before it's, everywhere, the benefits, they're huge, right?
Yeah.
Faster speeds, lower energy consumption, longer lasting devices.
I mean, how can you argue with that?
Yeah.
This has been a really, really fascinating deep dive. I think we've all learned a lot about this incredible new memory technology.
Me too.
And it's always amazing to see how scientific curiosity and ingenuity can lead to these breakthroughs that have the potential to really change the world. So thank you so much for joining us today and sharing your expertise on this.
Oh, it was my pleasure. Thanks for having me.
And to our listeners, keep those curious minds engaged, keep exploring the world, keep asking questions, and who knows, maybe you'll be the one to bring us the next mind-blowing topic for a deep dive.
Until next time.